Shalom, hello everyone. So, welcome back to our videos on turbulence modeling. So, in the last video, we were talking about the C1, C2, C3, and C4. And now we want to compare this G, which is used in OpenFoam, against this G, which is used by Grigson. Alright, so what I will do is to quickly put all of this into some form of Excel spreadsheet, because it's really hard to compare this function to this function analytically, just like we did for the smooth surface. So we'll need to at least compare it numerically. So to do that, we'll just put all of these into Excel. So I've made an Excel spreadsheet with T1, T1 and T2 and C1 to C4. Okay, so this is the value of G. So I'll bring you through the spreadsheet in a little bit. Okay, so ignore everything else and just focus on this. So I made headers. One called roughness constant. The next column is roughness factor. You can just ignore this for the time being. And then I'll have C1, C2, C3, and C4. For roughness constant, I put a default value as 0.5. Roughness factor, well, we can just start at 1 first. Alright. What is the roughness factor? Remember, the roughness factor is this constant we put in front of HS. So if you remember this formula, this is where the roughness factor comes into play. So this KS plus equals to some roughness factor times HS plus. So I'll just copy and paste this. Alright, copy and paste this down. Yeah, copy and paste this down. And yeah, KS plus equals to some roughness constant into some HS plus. So that is what we have. Where this roughness constant comes from. So this is the roughness. Okay, no, there's roughness factor. This is the roughness factor. So roughness factor is this one, where it's the scaling one. Roughness constant is another empirical constant, which you will find in here, in C1 especially. In C1 there is this K roughness, which is the roughness constant, not the roughness factor. So this will be where you put the 0.5 by default. And OpenFoam kind of suggests us to use a roughness constant of 0.5. Alright, so that's where we are. Okay? So this is C1, C2, C3, and C4. So what is C1? C1 is 1 divided by 90 minus 2.25 plus the K roughness, the roughness constant. So I put here, you see on here, the formula is 1 over 90 minus 2.25, and then I add to it the roughness constant in cell H5. I lock it, of course. So this is over here. Next one is C2. C2 is 2.25 over 90 minus 2.25, and if you see the formula here, 2.25 over 90 minus 2.25. C2 isn't too difficult. So now, next we want to look at C3. C3 is slightly more difficult, which is 2 times arctangent of 1 over ln 90 over 2.25. So what is the formula here? It's 2 times arctangent 1, or we call it A10 in Excel, divided by the ln of 90 over 2.25, the natural logarithm. So this is what we have here. Again, C3, well, you have the arctangent. It is basically just a constant with this number. Nothing too fancy there. C4 equals to C3 times ln 2.25. Alright, C3 times ln 2.25. So this is C4. I just have ln 2.25, the natural logarithm ln, times L5. So L5 is the cell which I put the value of C3 in. So this is my basic So we have that, and now we can start trying to put together T1 and T2. So we can put together this G function. So T1 equals to C1 into Ks plus minus C2. T2 is C3 into ln of Ks plus minus C4. So again, we'll need to do some Excel bits. So what I did is, okay, I started with this column, Ks plus, from the value of 2.25 all the way up to the value of 90. So that's the range that we are interested in. I mean, above that, the problem is relatively trivial. I mean, compared to this, we just have to have a 0.5 times F roughness should be equals to this constant. Okay, so okay, this one I kind of didn't do the calculation, but if you want to see what the value of F roughness is 0.2638. Okay, 0.2638 divide by 0.5. So at the end of the day, F roughness is about 0.5276. So this one is basically you multiply it by 2, then you get the number. Okay, so that's as long as we set F roughness is as this and the K roughness as 0.5, then we are set. Okay, so what I did is I do this KS column first, because that will be used to plot the G of this. Okay, so this is based on KS. This one's the one in OpenFoam. However, of course, G in the standard way we kind of write it, it's based G, the standard G that we find in the conference paper, the Grigson G, is based on HS plus. So I kind of needed another column just to prepare for HS plus as well. But that one I'll talk a bit later. Let's see how we can do T1 and T2 first, and we get this G. So T1 is C1 into Ks plus. So I have a column of Ks plus here. So T1 it is, okay, I will have C1, which is in J5, cell J5 here. I lock the cells using the F4 function key. So if I press F4 now, you can see that I can change the way J5 locks. So anyway, yeah, press F4 to do that. So that's C1. Then you times R5, which is the Ks plus. So C1 into Ks plus minus C2. C2 is here, which is K5. And I lock the cell. And then I just do a simple pull down over here, and it will give you the correct values. T2, we do something similar. C3. Okay, so press F2 on that to give it the kind of what do you call it? To just give it the form to show, make it show the formula. So C3 times logarithm. So this is L5, which is where the C3 value is, and then logarithm of natural logarithm of R5, which is the Ks plus, minus C4, which is found in cell M5. Again, I use F4 to lock both of these cells, and I'll just press enter, and basically I'll just do that. After that, it's pretty easy from there on in Excel or whatever spreadsheet program you want. So I have ln of T1 times sine of T2. So the formula is this: ln of T1, which is in S5, and sine of T2, which is in T5. Okay, so I'll do this, and I'll just go all the way from Ks equals 2.25 all the way to 90. So that's where we get this G from the OpenFoam for the wall function. So it will start from 0 because remember in the third regime for Ks less than 2.25, we have a smooth wall treatment, so this whole roughness function thing should be 0. Okay, and yeah, so that's how we get these values. So if you want to compare against the Grigson G, which is the one that we are used to from the paper that is found here. This one is by Grigson, that's why I say it's a Grigson G. So this is actually the delta U plus times this von Karman coefficient 0.41. So this Grigson G here, it is this logarithm I'm highlighting over here. So this is what I'm highlighting here, and I want to plot this as well. However, it does not use K plus, it uses HS plus. And HS plus and K, remember, they differ by just a factor of this K roughness or F roughness, the roughness factor. Alright, so I will have 0.5, okay, F roughness F roughness times HS plus equals to KS plus. Okay, so this is what it is. KS plus equals to F roughness times HS plus. So in other words, if I want to get HS plus, I will just use KS plus divided by F roughness. Alright, so that's what I do. This one divided by K roughness, so HS plus equals to KS plus divided by the F roughness. So I have KS plus in cell R5 over the roughness factor, which is over here. This is the K roughness or roughness factor. I'll just do enter and then I drag it down like so. And once I've done that, I move on and we have this G Grigson, which now I will just say, based on this is just the logarithm of 1 plus HS plus, which is in Q5, divided by exponential 3.25 times 0.41, where 0.41 is this von Karman coefficient. Yeah, so it is exactly the formula you see here. So now I want to plot it to see how they correlate. And basically, in this chart, this is a scatter plot between, let's see. Now this is a scatter plot between, let's say, yeah, the G Grigson, which is this blue curve, compared to the G in the OpenFoam. You can see they roughly match very well, except at the start and the end they don't match very well under the given constants and parameters, right? So given the roughness factor. So I mean the shape is more or less the same. So I mean, if you want to use a default roughness constant, roughness parameter of such, you can do so, but do know that you are subjecting yourself to some kind of error. So one possible workaround is this. All right, one possible workaround is this. Remember, we can change our roughness factor. So for example, we change it to 0.9. All right, and let's see whether this curve actually changes. Okay, the curve didn't change much. I will just put it here. So we can play around with the roughness factor. So you see the curves, and they start to match more closely as I decrease. 0.7. So closer and closer matching. Though of course note that the axis changes because the range of HS plus actually kind of changes. So yeah, we can go down even more. Alright, you can go down more. 0.5 even. 0.5, you can see it matches very closely. Now remember just now inside our document, we showed that we can get in this KS plus more than 90 regime, we can get both of these to match. We can get both of these values to match exactly if the F roughness, the roughness constant, is equals to 0.5276. So if we key that in, if you're wondering why I had this 0.5276 there, it's just for me earlier to test what is the value of this constant, and I can just type 0.5276, enter. and you'll see something pretty interesting. All right, pretty much at the beginning, there will be this same gap. We'll discuss that in a while, but you see towards the tail end, it matches pretty much exactly. So G plus equals to G Grigson. I mean, at the end of the day, you see this, both of them are about 3.827 or 3.8287 or 3.8286. So that's where we have very close matching there. So the roughness factor at 0.5276 does give you a very good matching at a high Y plus value. Okay, so that HS plus at 170, it will give you such a value. Okay, of course you can use different factors as and when you fancy, but of course something over 0.1 will give you a pretty off thing. Likewise, if you try and put it at 2, again you'll get really awful looking curve. So I mean, the qualitatively the nicest looking matching curves are found at 0.5276 roughness factor. So we can just stick to that. And this actually has the added bonus of ensuring that these constants actually match exactly in this third regime, where Ks equals to 0.9 or more than 90, Ks more than 90, Ks plus more than 90. I'm sorry. So yeah, that's what the Excel plots show. I mean, if you're okay with that, then sure. Now I want to talk about the about this factor here. This factor towards the beginning. You look at this, there's an offset between the Grigson G and the OpenFoam G. So why does the OpenFoam G have this offset? So remember that at 2 Ks plus equals 2.25, the OpenFoam G is exactly 0, because anything below this value we consider the wall smooth. But this Grigson value only tends to 0 at HS plus equals to 0. Okay. So this Grigson G tends to 0 at HS plus equals to 0. Because when HS plus equals to 0 here, this whole expression just becomes the logarithm of 1, and then it truly becomes 0. Whereas, for OpenFoam, it kind of separates it into 3 regimes, where Ks plus less than 2.25. Then we have the second regime and the third regime. So they kind of have this differential in the beginning, which no matter how you change your roughness coefficients, it won't really match because of this offset. Because the G of Grigson will always be non-zero at this point, and the OpenFoam G is actually 0 at Ks plus equals 2.25, and Ks plus equals 2.25, and as for me, I find this setup pretty comfortable, because the curves really match well, at least in the dimensionless constants, so that this G value, it matches pretty well, especially at high HS plus values. Okay, of course the disparity grows over here, which is unavoidable, but otherwise the trend of the curve and the shape of the curve, it does match really well. So at the end of the day, Ks plus and HS plus will work. I mean, if we use F roughness equals to 0.5276 and K roughness equals to 0.5, we can sort of get reasonably good results. Okay, so this is derived from the roughness wall function over here, provided by Grigson, and is obtained from Colebrook's data. So Colebrook, he did some boundary layers studies with a rough surface roughness. So remember that this expression is just empirical and it comes from Colebrook's data. If that doesn't quite match the setup you're having, then you have to think twice about the accuracy. But of course you can tweak it as you want by playing around with these two constants so that you kind of get the correct graph matching. But these two constants at these values, f roughness equals 0.5276, k roughness equals 0.5, these constants match Colebrook's data reasonably well. And we know that in the regime of, what do you call that? The regime where ks plus more than 90. Okay, so ks plus more than 90 is, where is it? Yeah, I think this is the one. Yes, this one. I shall just bold it. So the region where k is plus more than 90, we are sure to match because yeah, if k roughness equals this much, then yeah, we can get it. But we want k roughness to be 0.5. So we can get the f roughness, we can adjust it by adjusting f roughness. Then we have f roughness equals 0.5276. So this is it for this video. Yeah, I am, yeah, surprisingly, yeah, it's it matches pretty well. It's pretty satisfying to see the OpenFoam data and Grigson data matching. So now you know how to kind of tweak and calibrate your f roughness and k roughness to try and match different data sets. So you can do that for your own wall function, and you can tweak it as you want. I've shown you how already, so yeah, hopefully this helps you when you are using wall functions to handle surface roughness. Okay, so that's all I have for you this video. In the next video, we will hopefully explore other topics, different models of turbulence as well. Yeah, I'll see you guys next time. Thanks for watching. Bye bye.